Hello students, in the first lecture of this chapter, we had defined homomorphism, epimorphism, isomorphism, endomorphism, automorphism, and isomorphic groups, and homomorphic images and kernel of a group. Now in this lecture, we will solve problem based on that to understand the terms. So the first problem is, let Z be the group of all integers under addition. So Z with binary conjugation prediction. And G consists of 2 raised to n where n is a integer. Be a group under multiplication. Z is a group under addition, integer addition, and G is a group consists of 2 raised to n where n is integer. Integers, these are both are infinite groups. First group is under binary conjugation addition, and second group is binary conjugation of multiplication. And we have defined a mapping f from Z to G, Z to set of integer under addition to set of numbers to use for n where n is integer by how we define this mapping? This will define f of n is equal to 2 to n for all n belongs to n. Our aim is to show that the mapping f is isomorphism and find the kernel of f. Our aim is to find kernel. So solution is what is given. Mapping f is a f is in we have to show that f is in isomorphism. What to show? And show it is f is in homomorphism and f is 1. And we have to third is we have to find the kernel of f. So given is what is given? Given is f is a mapping from Z to G. In Z is a set of integers under value addition, and G is the set of 2 for n number. 2 to n is integers. Numbers 2 to n is integer defined by f of n is equal to 2 to n for all n equals to n. Z is what is given. Z is a group under addition of integers, and G is a group under multiplication. So we are given both sets are different time composition. Our image shows f is a homomorphism. F is a homomorphism. So let us take n1 and 2 belongs to the domain G, Z. Again, if they belongs to Z, then f of n1 will be 2 to n1 and f of n2 will be 2 to n2 belongs to G. Now when we show f is homomorphism, I have to show what the binary coefficient in Z is addition. So we have to show that f of n1 plus n2 is equal to, but by the definition of mapping, how to write it? Is equal to n1 plus n2. Separate them, base is same. This can be also written as 2 to n1 is equal to n2. So 2 square n1 is equal to f of n1 and 2 to n2 is equal to f of n2. So f of n1 plus n2 is equal to f of n1 into f of n2 implies f is a homomorphism. Now second we have to show that f is 1 1. F is 1 1. Let n1 and n2 belong to Z such that f of n1 is equal to f of n2. However, we need to show that n is equal to 2. So substitute the value f of n1 is equal to 2 to n1, f of n2 is 2 to n2. So these two numbers are equal if their powers are equal. N is equal to implies n1 and equal to Z and f of n1 is equal to n2 implies f is 1 1. F is 1 1 as well as f is homomorphism. Therefore, f is isomorphism. Now, I will find the kernel of f. Since we know that 2 is for 0 is 1, is the identity element of G. So, kernel of f is defined as the set of n belongs to Z such that f of n is equal to 1. That is, n belongs to Z such that 2 square n is equal to 1 is equal to 0. So, n comes out to be 0. So, kernel of f consists of 0 element only, identity element. And the values of x. Now, the second problem is let Z be the group of integers under addition, and G consists of two elements minus 1, 1. Be the group under multiplication. Show that the mapping F from Z to G defined by f of f of n is equal to 1 if n is even, and this to minus 1 f is n is odd. When we get what we show, is a homomorphism but not an isomorphism, and also find the kernel of. So we have to show this is a homomorphism but not isomorphism. We have to show that this mapping is a homomorphism but not one one. So given is f is a mapping Z to G defined by f of n is equal to 1 if even, minus 1 if it's odd, and here Z is a group under addition under the binary condition of addition, and G is a group under the addition of multiplication. So let us take n1 and 2 belongs to Z. Again equations. Three possibilities will arise. The both n1 and 2 are odd integers, both are even integers, and either of two are even, or either of two are is either even or odd. The first possibility, the first case is here. When n1 and n2 both are odd integers, then the sum is a even integer. So f of n1, if n1 is odd, f of n1 is equal to minus 1. Definition of the matrix f of n2 is equal to minus 1, but f of n1 plus n2 is equal to 1. So f of n1 to f of n2 is equal to minus 1 to minus 1 equal to 1, 1 is equal to f1. So f of n1 into f of n2 is equal to f of n1 plus n2, implies f is a homomorphism if both the n1 and 2 are odd. Similarly, case second, when n1 and n2 both are even integers, then the sum is even integer. So if n1 is even integer, the sum is even, then the value, then the mapping f of n1 is equal to 1, f of n2 is equal to 1, f of n2 is equal to 1. So again, find f of n1 to n2. In order to show that it is a homomorphism, take f of n1 to f1. f1 is equal to 1 into 1, 1 is equal to f of n2, f of n2. So f of n1 into n2 is equal to f of n2 is equal to f of n1 plus n2, implies f is an homomorphism for if both the n1 and n2 are even integers. Third case, when one of the n1 and 2 is even means other will be odd. Let us suppose that n1 is even, and if any of the two is even, therefore sum is odd. So let us suppose n1 is even. So f of n1 is f of n1 is odd. F of n1 will be minus 1, and other is even. So f of n2 is equal to 1. So f of n1 plus n2 is minus 1. So again, find f of n1 to f of n2. In order to show is a f mapping is a homomorphism. F of n1 to f of n2 is equal to minus 1 to 1 is equal to minus 1 minus 1 equal to f of n1 plus n2. So f again f of n1, if either of the two n1 and n2 is either even or odd, f of n1 into f of n2 comes out to be f of n1 plus n2, implies f is a homomorphism from Z to G. Now, second part to show f is not 1. F is not 1 1. So let us take n1 is equal to 3 and n2 is equal to 5. Both are odd integers. Or you can take another example also. That is n1 and 2 both are integers and both are odd. So f of n1 is equal to f of 3 is equal to minus 1. F of n2 is equal to minus 1. So f of n1 is equal to minus 1 is equal to f of n2. But f3 is not equal to 5. There are so many examples to show this. So f is not 1 1. We have shown a counter example. So f is homomorphism but not 1 1. Therefore, f is not an isomorphism. Therefore, third is kernel of f. Since one of the identity element of G, one is the identity element of G, then kernel of an f in G is the set of all n belongs to Z such that f1 equal to f of n is equal to 1. Since f of n is equal to 1 for all even integers, therefore kernel of f consists of 2Z. Z is integer for all even integers. Question is, let Z and E be two groups of all integers and even integers under addition. Under integers under addition. Then show that the mapping f from Z to E defined by f of x is equal to 2x for all x belongs to Z is a homomorphism. Is it an isomorphism? So whether it is 1 also, and also find the kernel of f. Given is f is a mapping from Z to E defined by f of x equal to 2x for all x equal to Z. Now we have to show that this is a homomorphism. Let us take x belongs to Z. Therefore, x plus y also belongs to Z. So f of x plus y is equal to definition of the mapping. F of x plus y is equal to twice of x plus y. This can be because x and y integers, therefore it can be written as 2x plus 2y. So the f of x plus f of y. So f of x plus y is equal to x plus y implies f of x plus f of y implies f of y implies f is a homomorphism. F is 1 1. F is 1 1 or not. Let us take x equal to z such that f is f of y. So 2x is equal to y. So this will hold true if x is equal to y. So it implies f is 1 1. So this mapping is first and second. F is a homomorphism. F is 1 1. So f is an isomorphism. So now we will find the kernel of f. Since 0 is the identity element of the group of even integers, therefore kernel of f is the set of all x into g such that f of x is equal to f of x is equal to f of x is equal to 0. So x into g such that 2x is equal to 0. 2x is equal to 0 if x is equal to 0. So kernel of f consists of the only 0 identity. Okay, let C and R be the groups of complex number and real numbers respectively under addition. And on both the groups, set of complex number, set of real numbers, addition. Define a mapping f from C to R such that f of x plus y equal to x. First is the real part for all x plus y belongs to C. Prove that f is a homomorphism. Is it an isomorphism? Also find the kernel of this. Given is f is a mapping from C to R defined by f of x plus y equal to x. Now I will show f is a homomorphism. So let us take two elements z1 z2 belongs to C. So if a z1 z1 to C, then z1 is a plus iota b, and z2 is a plus c plus iota d, such that f of z1 is equal to f of a plus iota b equal to a, f of z2 is equal to f of c plus iota d is equal to c. Then z1 plus z2 will be a plus iota b plus c plus iota d is equal to a plus c plus iota b plus d. So f of z1 plus z2 is equal to, because both the groups have been different addition. F of z1 plus z2 is equal to f of sum is equal to a plus c. F of a is equal to f of plus iota b. F of c is equal to f of, so f of z1 plus z2 is equal to f of z1 is equal to f of z1 plus f of z2. So implies, therefore f is a homomorphism from C to R. Now I will show f is not 1. It means it is not whether it is 1 1 or not. So let's say z1 belongs to is equal to 3 plus 4 iota, and z2 is 3 plus 5 iota. Both are complex numbers. So f of z1 is equal to f of 3 plus 4 iota is 3 is equal to f of, can also written as f of 3 plus 5 iota. It also gives 3. So f of z1 is equal to f of z2, but z1 is not equal to 3 plus 4 iota is not equal to 3 plus 5 iota. So f is not 1 1, hence f is not an isomorphism. Now to find kernel of f, since 0 is the, we have addition is the binary coefficient both the sets. So since 0 is the identity element of additive group of real numbers. Therefore, kernel of f consists of all z belongs to C such that f z is equal to 0. So z is equal to x plus eta y belongs to C. X and x belongs to C, they x and y real number. So this is equal to f of x plus eta y is equal to 0. So for this to be 0, x plus eta y, where x is real number such that x is 0, x is equal to 0. For x 0 means if you put x is equal to 0 in here, then kernel of f consists of minus eta y. So this implies the set of all the purely imaginary numbers, including the real number g, are the prime numbers. Next problem is for a fixed element b of a group G under the magnitude multiplication defined by f of b is from G to G. F of b is a fixed element by f of b of x is equal to b inverse xb for all x. Show that f of b is a automorphism. Yeah, given is given a for a fixed b belongs to G, define f b vector from G to G by f of bx is equal to b inverse xb for all x. Our aim is to show that FB is an automorphism. That is, F is homomorphism, F is 1, 1, 1, and naturally F is 1. So let us show, we have to show these three in order to show that FB is an automorphism. So first let us show that FB is an isomorphism. That is endomorphism. Isomorphism from homomorphism from same group to same group is a endomorphism. So let us see two elements. So f of fb of x plus y, xy is equal to definition of the inverse x y b. Put e in x and y. E can be received b inverse. So if you replace it in associative law, because g both g is equal, so b inverse x b, then this contains b inverse y. B inverse f b is equal to f b. B inverse x b is equal to f bx. B inverse y b is equal to f by. So f b of x y is equal to f b of x equal to y implies f is an homomorphism. That is because both the groups are domain and range groups are same. Therefore, it is a homomorphism. Now, our second is this. We will show that f b is 1. So let us take two elements x y belongs to G such that f b of x is equal to f b of 1. Substitute the values. B inverse x b is equal to b inverse y b. G is a group cancellation of whole string. Apply left cancellation by b left cancellation by b. So b into b inverse equal to e into x equal. This becomes equal to x b is equal to b. And applies right cancellation by b inverse. Implies x y. F bx is equal to f by implies x equal to y. F is this mapping is 1. Now we will show f is on. For all x belongs to G, there exists b x plus b belongs to G such that f b of b inverse x b is equal to, how can I by tapping this? So b inverse x b inverse b x b inverse x b x is this is equal to this. So b inverse is equal b inverse b is equal to e, b inverse b is equal to e into x is equal to x. So f b of b inverse x b is equal to x implies f is 1. First, second, f is endomorphism, f is 1 1, f is 1 2 implies f is an orthomorphism or isomorphism from G to this side. Thank you.